I hope you guys enjoy the Holi as well. So let me start today's tutorial. So I going to solve the assignment problem that has been given previous year after the second week, and in that week the whole course is about lecture series is about the thermodynamic relations coming from entropies. So now we will solve this first question. So in this first question it is asked, if suppose okay I am so I have no access to this portal, so today I will upload that things today from I think from tonight you can access the slides actually. Okay. Okay. Yeah, okay. I will upload by tonight. So yeah. So now the question is asked here that if there is a function fx which is equal to f of minus x, that means it is a even function. So even function. Now we have to verify that, as in the course it actually proved that it has been proved that this limit lambda tends to 0, lambda n equal to 1 to infinity, f of lambda n is equal to 1 by half minus infinity to plus infinity dx fx. It is a theorem. So it has been proved in the lecture series. Now the question is asked here that if suppose we have a function fx which is 1 by x square plus a square, which is actually a symmetric function, to explicitly check that from this summation and this integration both are giving same result. So let's start. Our function is fx is equal to 1 by x square plus a square, right? Now let me write it in another fashion, right? 1 by x square minus I a its square. I can write it always, right? Now we can also write it in this way, that 1 by x minus I a x plus I a. Now I can divide this 2ia into 2ia by x minus ia x minus ia into x plus ia. So this question actually very tedious in terms of mathematics. So we have to do it by step. So this is x by ia minus x minus ia x minus ia x plus ia. So now you can write it in this way, 2ia 1 by x minus I minus 1 by x plus I. Right. Now we have to calculate the value of this sum at limit lambda tends to 0. So what is the summation here? Summation is equal to n equal to 1 to infinity f of lambda n. So in place of x we'll put lambda n. So that means the series will become n equal to 1 to infinity 1 by 2ia into 1 by, in place of x we will put lambda a minus a lambda minus ia minus 1 by n lambda minus I. Right? Now if we take common this lambda from this both side, from these two equation, we will get 1 lambda, so that will be summation of n equal to 1 to infinity. Let me check. If I take not lambda, so x, so it is n lambda square. So if I take lambda here, so it will be, should be lambda square. Okay, it will be, if I common 1 by lambda here, 1 by 2i a lambda is lambda, then 1 by n minus I a by lambda minus 1 by n minus I a by lambda. So that means that means we need the summation, we need some closed form solution, closed form limiting value of this summation over n. So now, so to get a closed form solution, there is a trick. Without that trick you can't do the summation actually. So the trick is, so to know, after knowing the trick, so we have to know a function called digamma function. Digamma function. So digamma function. What is the digamma function? The digamma function is nothing but the derivative. Suppose that psi z is equal to digamma function is nothing but t dz of gamma function. It's the first derivative of the gamma function. What is the gamma function? Gamma function actually will take the form z factorial when z is integer and z greater than 1. So this is the basically form of the digamma function. Now why I am writing this digamma function? Because these digamma function of 1 plus z can be written as minus gamma. This gamma is actually is a irrational number, is actually order of 0.57. It's actually value of 0.57 plus summation of n equal to 1 to infinity 1, actually it's okay, n equal to 1 by infinity 1 by n minus 1 by this z plus n. Right? Now you can see why I am introducing this digamma function, because you know I have to know the closed form of the summation 1 by n minus I a by lambda. There is a plus sign, I missed it some, this is a plus. So we have to know the closed form solution of this. So you can easily read from here that it is nothing but 1 by n minus 1 by zn plus z plus n. So this is the things, n plus z, summation of n plus z can be written in terms of diagonal function, a constant, and series of n equal to 1 to infinity 1 by n. So, and there is another property of the diagonal function is diagonal function of 1 minus z minus of z is equal to pi cot pi x. So we will later, you will see that we will use this relation, and there is another relation also we need is psi of 1 plus z psi of 1 plus z is equal to psi of z plus 1 by z. Hello, Muktalakshmi, can you yeah, thank you. So this property we will also use this property as well. So let me use this property and write my summation n equal to 1 to infinity in terms of, so let it represent it this way, that my this will be, I can write it actually in this way, 1 by 2 ai lambda summation n equal to 1 to infinity, I am adding n 1 by n and minus, so basically I am doing nothing, I adding 1 by n and also subtracting 1 by n. So if I add 1 by n, so it can be adding and rearrange, then 1 by n plus ia by lambda minus 1 by n, so my 1 by n cancelled out, and then what is remained is 1 by n minus I by lambda. So I am doing basically nothing, I am just adding and subtracting 1 by n and basically rearranging them, minus ia by lambda. Now you can see that I can use directly this formula, because now it is in this form. The summation of this term will give me a diagonal function, and also summation of this term also give me a diagonal function. Write it in this in terms of diagonal function. So I will get here what is the diagonal form? So 1 by n minus z plus n, that will be psi 1 plus z. So here that means this will be psi 1 plus ia by lambda, and this will be the value of this will be gamma, digamma function plus gamma. So that means it plus gamma minus, this can also be written in the same fashion, that means gamma minus psi of, this is actually z here, this is the n and this is z, so 1 minus z is here, my z is minus a by lambda. So if I, that means I got these two terms, one is psi 1 plus ia by lambda minus psi 1 minus ia by lambda. Now what property I should use? I will use the property here, this property. Why I will use this property? Because I know psi of 1 minus z minus psi of z is pi cot pi x, pi cot z, sorry, this is actually z, pi cot z. So I will use this property. So if I use this property, 1 by 2ai psi of 1 plus z will be psi z plus 1 by z. Psi z means here z is here, this is z, this is 1 plus z is equal to psi z plus 1 by z. That means psi of ia by lambda plus 1 by z, 1 by I a by lambda. So there should a lambda should be here, there lambda is there, so that's that. Is it right? Right, psi z. So I will retain it like this, I by a minus psi of I 1 minus a by lambda. So now this psi a by lambda, and I can now directly use this formula. So if I use this psi 1 minus z minus psi of z, here psi of 1 minus z, here I should be there somewhere, I. So this if I written there, so this will be psi of z minus, here minus plus, so this will be minus, so psi of z minus psi of 1 minus z, it should be minus cot pi z, 1 by 2 ai lambda into 1 pi I a by lambda minus cot, sorry, this is pi cot pi z by lambda, cot pi z, cot pi z. Here what will be z? Z will be nothing but I a by lambda. So now we will expand this cot pi z, cot pi I, cot pi I a by lambda. I can write it in this way, pi cot pi into pi, this is cos I pi a by lambda pi sin I pi a by lambda. If I expand the cos is in terms of x Euler series, it expand in terms of e to the power, that means e to the power I into, we know that cos theta is equal to e to the cos theta is equal to e to the power I theta plus e to the power minus I theta by 2, as well sin theta is equal to e to the power I theta minus e to the power minus I theta by 2. So if I put it there, what I will get? Plus I theta, so that means that will get pi a by lambda plus e to the power minus I pi a by lambda pi e to the power I pi a by lambda minus e to the power minus I pi a pi lambda, here 2i, so in there is a 2i, so I will be multiplied here. So now I pi, what it will be become then e to the power minus pi a by lambda plus e to the power plus pi a by lambda. So you may think that it is very hard to do, but at the end of the day you will see that there is a beautiful result is there, because this summation is actually converges to pi by 2a. So I will go to that answer. So to going to that answer, we have to do all the steps. 1 by, it is that e to the power minus pi a by lambda minus, there is a 2i about e to the power plus pi a by lambda. Right, now you can do the following. It basically nothing 1, so one can do these things. Yeah, so these could be written as, simply if we multiply both sides with e to the power pi a by lambda, up and down, if we multiply upper side with e to the power pi a by lambda, downside also pi by lambda, you will left with e to the power, so this is basically you will get e to the power 2 pi a by lambda minus 1 plus 2, e to the power 2 pi lambda plus 1, you can break it into parts, and e to the power 2 pi a by lambda minus 1. So basically we get 2 pi I lambda, no sorry, we'll actually get this, so I pi 2 by e to the power 2 pi a by lambda minus 1 plus, so there will be a minus sign, right? Here it is actually minus, it is actually plus, so it is actually minus, it's actually plus, so plus it is I pi. So now I can put it here, so if I put it there, what I will get? I will get 1 by 2 ai lambda into 1 by ai lambda minus, so lambda will be upper, so ai pi lambda plus I pi plus 2 pi I by 1 minus e to the power pi 2 pi a by lambda. Now it is almost done. Now what is our asked question is limit lambda tends to 0, lambda multiplied with this summation. So if I multiplied lambda, what I will get? So what I will get, let me see that. So if I limit, now I will take the limit lambda tends to 0. If I multiply lambda with that, that means this will be cancelled, so that will be 1 by 2 a, lambda will be cancelled because I multiplied lambda as I just calculate the value of the summation, but in the question it is asked the limit lambda going to 0, lambda into this summation, so I have to multiply lambda. If I multiply lambda here, it I and I am taking the I inside, so here this will be minus, it will be minus a by lambda, right? Or you can lambda, you can write it lambda in the up, so this is basically nothing but lambda by a plus I pi plus 2 pi I cancel actually, so I is not there, by all real, it should be there all real, 2 pi a by lambda. Now the beautiful thing is since lambda tends to 0, that means a by lambda, that is here, that is a by lambda tends to infinity, and if it tends to infinity, that means this whole term tends to 0, because it as a by lambda tends to 0, that means e to the power 2 by a by lambda should also tends to 0, it tends to infinity. Now 1 by e to the power 2 pi a by lambda, since it tends to infinity, that means it tends to 0, so we can neglect at the when the in the lambda going to 0 limit, this term actually go to 0, and since lambda is 0, basically a is finite, this term also going to 0, so what I am left with is actually pi by 2a. So that means if I going by this route and calculate the series sum, what I will get, limit lambda tends to 0, lambda n equal to 1 to infinity, f of lambda n is actually lambda by 2a. Now since we have done a tedious mathematical work, but extract a very small result. Now the beauty of this formula, you can see from here the beauty of the formula. Now the theorem, as in the course it is said that there is a theorem which says that limit lambda tends to 0, lambda is equal into lambda into this sum as actually can be written as 1 by 2 half into minus infinity to plus infinity dx fx. So that means if we can also do these things to calculate the limiting value of this series when lambda goes to 0, as we convert it into an integration, and then if we do the integration we should get the result that we had written there, this pi by 2a. So tx fx, what is the value of fx? We know x square plus a square, right? So x square plus a square. Now we can write it here half, since this function since x 1 by x square plus a square is actually even function, then we can write it as 0 to infinity dx by x square plus a square. And what it is? It is nothing but 1 by a tan inverse of x by a, limit 0 to infinity. If I put it there, that means 1 by a tan inverse of infinity minus tan 0, and we know that tan infinity is nothing but pi by 2, that means pi by 2a. Only by doing 3-4 step we actually tell the what is the limiting value of this tedious looking series, which is the limiting value series, that is actually pi by 2a. Now we have done that. If we go to this, if we use the theorem and convert it into a integration, then we will get the result same as if we not use the theorem, and by brute force by doing this all the step and see the series actually going to reaching towards the limiting point, which is actually pi by 2a. So that means we actually calculate these things, that means that the limiting tends to 0, this answer should be pi by 2a. So now when you will see in any exams that as one of you suggested, asked me that you are going to prepare for the just exam, so it may be some question may be there that that is asked that find the limiting value of this series. Now since you know that at lambda tends to 0 this series always converge to this integration, so you don't have to worry about this series. You only have to use this theorem and write it in terms of integration form, and you will actually easily calculate the limiting value of this series. Now in the second question, the first question we have done, now the second question it is asked the same things for fx equal to e to the power minus x by a. It is actually very easy. So let do for the second question, where summation of n equal to 1 to infinity, here the fx is equal to e to the power minus mod x, maybe mod x or mod x by a, mod x by a. Now here that means it will n lambda by a, since my lambda is actually greater than 0, and here I taking the lambda is my greater than 0, I am let lambda greater than 0, and we know that n also greater than 0 because n is positive integer. So basically we can write it here, this modulus is actually nothing but x, so it is minus n by lambda, n to infinity. So this sum actually is easy. So this is basically this sum. If I take this lambda by a, so I left with 1 plus e to the power minus lambda a plus e to the power minus 2 2 lambda a plus dot 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 up to infinity. So we know that this is nothing but 1 minus e to the power minus lambda by a. Okay, so you can write it here as well in terms of that also. What it is 1 by, if I multiply both side with e to the power lambda by a, it will look like e to the power lambda by a minus 1. Now what is the limiting value of lambda tends to 0? Lambda into this will be 1 by e to the power lambda by a minus 1. So you can see that if I put lambda above and below, these two become, both the numerator and denominator both will become 0 by 0. So 0 by 0 form is, we know that it is undetermined, so we have to use the L'Hospital rules, which is actually this will be derivative with respect to lambda. Derivative, if I take derivative lambda, this will be 1, and derivative with respect to lambda will be 1 by a e to the power lambda by a, right? So a up and e to the power lambda by a. Now I can limit tends to 0, limit lambda tends to 0. I have done nothing, but I just use the L'Hospital rule that if there is a 0 by 0 form, suppose that we know that 0 by, if in the limit, if the 0 by 0 form appeared, we actually use the derivative of the upper and derivative of the down. So that will be limit lambda tends to 0, 1 by a e to the power lambda by a. So limit lambda tends to 0, a by e to the power lambda by a. Now if I put lambda equal to 0 in the lower case, it actually it is actually doesn't become 0, it doesn't become 1, it doesn't become 0, it's actually become e to the power lambda a. If I put it 0 here, that means it is 1. So that means this series, the limiting value of that series will be a. Okay, so first the left hand side we have done. Now it's time to do the right hand side. So in the right hand side, it is actually half minus infinity to plus infinity fx dx. So as fx is even function, we can write it here as, you can write it like 0 to infinity f of x dx. Since x greater than 0, we can write fx is equal to the power minus x pi a. So if I write it there, e to the 0 to infinity e to the power minus x by a dx, if I integrate it out, so it will become 1 by a minus e to the power minus x by a 0 to infinity. So if I put it there, so it will become at infinity it will 0 and 0 it will 1, so it will become a. So now again we can see from here that this left hand side and right hand side, actually for this also the left hand side actually become a and the right hand side also become a. And the third case, so that means here what it is matching, that this matching that for fx, left hand side is equal to pi by 2a, right hand side is equal to pi by 2a, fx equal to the power minus x by a, left hand side is equal to a, right hand side equal to a. We have to see the last one, that f of the function, what is the form of the function? Form of the function is nothing, that f of x is equal to a, is equal to 1, right, is equal to 1 if when x remain between a to a and otherwise 0. Okay, that means the function is become 0, fx becomes 0 at x equal to a, x equal to plus minus a. Okay, so we'll use that this thing to calculate the limiting value of this series. So limiting value of the series will be lambda n equal to 1 to infinity f of n lambda. Since we know that this as n lambda, since it is positive n lambda, so as n lambda will become a, is become a, this fx will 0. That means if n is equal to a by lambda, then this actually becomes 0. Then if n greater than a by lambda, for all n which is greater than a by lambda, this f of n lambda will become 0. That means we can write simply n equal to 1 to a by lambda, n equal to 1 to a by lambda, because all other n will contribute nothing, because f of that n will become 0. That means for all of these, for all of n which is actually less than a by lambda, 1 and n by lambda, which n will remain in this region, n equal to greater than 1 and greater than equal to 1 and less than a by lambda, this function will be 1 for that values of n's, and for other values it's actually becomes 0. So this summation is nothing but lambda into all. If I sum 3 1, it will give 3. So if I sum a by lambda 1, so it will give a by lambda. That means it is actually become a. That means the left hand side of this, for this fx is actually become a. Now let check that what is what the value is for the right hand side. So right hand side is nothing but right hand side half 0 minus infinity to plus infinity fx dx. Again it is a even function, so we can write it 0 to infinity fx dx. So this actually 0 to infinity, because all, since the functional form is like that, so that means it actually remain 0 to non-zero. The function will remain non-zero in the region 0 to a. So fx equal to 1 dx. So if we integrate it out, so it will become a. So now here also the left hand side, that means the limiting value is the summation and the value of the integration, both will become a. Now what is will be the answer? Now fx equal to this 2a, this, okay, the first one, actually the first one actually answer, because fx for left hand side pi by 2a, right hand side pi by 2a, fx e to the minus x by a, left hand side a, right hand side a. For this function also left hand side a, right hand side a. So we have done with this question. That means the correct answer for this is a. Now I will do the question number 2. So let me insert the question number 2. Problem 2. Yeah, so this is the question number 2. So does anyone have any question regarding these calculations? If there is no question regarding those calculations, then I will proceed further and I will do the question number 2. So in the question number 2, it is in question number 2, it is asked, it is given that SUVN, U is the internal energy, V is the volume, N is the total number of particle. So S equal to U comma V comma N is equal to N into S U by N, V by N 1. So since S is an extensive property of the system and UVN also an extensive property of the system, you can always write the entropy as like this. So it is written there. Now what it is asked? It is asked that so that this entropy function is extensive. Yeah, it is extensive for showing that it is extensive function. It is nothing. So let us show that explicitly. Now let us see that this extensiveness of this entropy explicitly. Is UVN is equal to N is U by N, P by N comma 1. Now if I scaled U to lambda U and V by lambda V and N by lambda N, what my entropy will look like is U prime v prime n prime is equal to n prime is u prime by n prime comma v prime by n prime comma 1. So since this is a scalar, so it will not if I change my coordinate, it will not change. So it will, so if I put it the value here, so it will lambda n, and since u prime by n prime is nothing but lambda u by lambda n, so it is actually u by n. Similarly u by n, and similarly v prime by n prime also v by n comma 1. Now you can see that lambda n and u v n, what it is? It is s u v comma n. So s u comma v comma n. That means if I scaled my system through a factor lambda, then this entropy should also be scaled as lambda. So as you can see, if it is extensive, if the entropy is truly extensive, then it should scaled with lambda. Since we actually scaled all the extensive property u, v and n with lambda, so you can actually see from here that this entropy actually scaled with lambda. That means entropy is a extensive function. So this entropy function, if I write the entropy function in this way, this entropy function actually extensive entropy extensive function. Now here imagine that the second question, the part 2 of this question is, imagine that for a certain gas s u v1 small u small v1 is equal to small u cube v square. Find the equation of state of this gas, okay, and find the find the ratio of r pv by nt. Okay, let do that. So it is given that s small u small v comma 1 is equal to u cube v square, right? Now u cube v square. Okay, now write it in terms of, okay, we write it in terms of uvn. What it will be? N multiplied by s u by n v by n and 1. So u by n is basically nothing but small u, it should be, yeah. So small u is equal to u by n and small v is equal to v by n. So alright, that means I can write it in this fashion. That means n into what it is? It is actually u cube by v square. That means u by n its cube and v by n its square. Okay, so that means n into u cube, sorry, this u will be pardon me, because my big capital U and small u all are looking same, so maybe the symbolize this will look somewhat messy. So u will be capital U by n, okay, u cube v cube and n to the power 5 n cube and 5. So that means u cube v, not v cube, v square, actually it is v square by n to the power 4. Okay, so as in the lecture, from the lecture we actually know that the three thermodynamic relation, one of them is P by T, actually P by K beta T, and we actually put K beta is equal to 1. So P by T will become del S del V with keeping U and N constant. So if I do so, what we'll get? We'll get 2 U cube, sorry, it's again capital V, capital U cube V. with respect to derivative with respect to v, to 2v u cube v by n4. So now I can write it again in terms of small u and v. So that will be u, so that will be u cube u cube into v. So they will be p. I use one relation, and the second relation is minus mu by t is equal to del s del n with keeping u and v constant. U and v constant, keeping u and v constant. What it will be? It will be with respect to n, u and v keeping constant. So that will be nothing but 4 by n to the power 5 u cube v square. So again we can write it as 4 small u cube v square. Okay, now another, this is the first relation for P, this is the second relation for the chemical potential mu. P is the pressure, by the way, here P is the pressure, T is the temperature, mu is the chemical potential, T is the temperature. And last equation 1 by T is equal to S by del U, keeping N and V constant. So if I derivative this relation with U, take derivative with respect to u, so it will become 3 u square, right? 3 u square v square by n to the power 4. So that means it actually 3 small u square small v square. Now they asked in the question, it is asked that we have to write it in terms of small v and t. That means we have to replace all u with v, small v and t. So we will use this relation to replace u. Is it correct? Yeah, it's correct. So it looks correct. Yeah, it's fine. So that means small v, we will replace small u because in the question it is asked that what is the first part of the question we have already done, what is the chemical potential of the gas and this pressure and the internal energy, all the things that we have to replace all the u by small v. So we have to calculate what is the energy per particle in terms of temperature volume. So this question we will handle first. So small u square, what it will be? It will be actually, let me check, something is not nothing, something is not incorrect. Oh, it's actually correct. So it's u square equal to 1 by 3t square is equal to 3t v square. That means u is equal to 3t to the power minus half into 1 by v. So that's it. So we successfully convert this u, actually write the u in terms of temperature and the reduced volume. Now, so the first last part actually has been done, and the second part, what is the chemical potential in terms of temperature and volume. Okay, let's check. Let us check. So chemical potential, minus it will be cancelled here. So chemical potential mu will be temperature that side, 4 into temperature small u cube v square, 4 temperature small u cube v square. So it is actually, if I put it there, value of the u, so it's 3t to the power minus 3 by 2 into v cube into v square, right? 40 3t to the minus 3 by 2 into v square. Okay, v square is there, v cube. Okay, so that's there. So it is actually 4 T into 3T to the power minus 3 by 2 into 1 by V. So the second part also run 4 into 3 to the power 3 by 2 T to the power. Okay, you can write it that way also. 4 into 3 to the power minus 3 by 2 T to the power minus half into 1 by V. 1 by V. And the third is, what is the relation of PV by NT? Okay, P by T. By using this relation, we have to use this relation to calculate P by T is 2 UQ by V. Okay, P by T is equal to 2 UQ by V. Okay, UQ by V. Now what is UQ by V? So PV by KT. Okay, PV will then replace U 3 to the power minus, okay, UQ means 2. Is it UQ? Is it UQ? Yeah, it is UQ. 2 UQV. 2 UQV. UQ means 3T to the power minus 3 by 2. Okay, 1 by V. So V 1 by V cube into V. So that means it will be P into 3T plus 3 by 2 into V square, right? So V square, that means, okay, now if I multiply PV by T, what it is? P into 3T to the power minus 3 by 2 into V means V by, actually I can convert this V into V by N into N, V square. This is nothing but small v. So small v, so this is not there, so that means it become 2 into 3T to the power minus 3 by 2 N is there into 1 by V. So let's check. So I can put it in there. So PV by NT is equal to 3T to the power minus 3 by 2 into, is it all right? That is all right. It's all right. 2 by, okay, 3 by V minus 2 by V. So nothing but I am writing it. Okay, no, it's not correct actually. So it is actually 2 by V. Yeah, 2 by V. That means you can write it T to the power minus 3 by 2 into 5 by V minus 3 by V. There is no point of written in this fashion, but as we have to match the answer with these keys, so you have to write in the fashion. So it's actually, we got the result mu equal to, let's check, mu equal to 4, 3 to the power minus 3 by 2, T to the power minus half V. So 4, so that means 4, 3 to the power minus 3 by 2 half. Okay, it's mu is there. U is 3 to the power T, 3T to the power minus half by half. So is it matches? U? Yeah, U it is matches. So and the last is P V by NT, 3 T to the power minus 3 by 2, 5 by V minus 3 by V. Yeah, 5 by V minus 3 by V. Okay. So that means the answer 1 is correct, as we have calculated that answer 1 is correct. That means PV by NT is equal to this, mu is equal to this, and U is equal to this. And the last question, what is the value of the R for the ideal gas? R is PV by NT. So let it check. So you can do it many ways. Since we all know the thermodynamics, so PV equal to, we know that N K beta T. Since K beta T equal to 1, so here beta t is equal to 1t, that means PV by NT is equal to 1, that means R equal to 1. So let it check from another relation that is called Sackur-Tetrad relation, Sackur-Tetrad form of the entropy. So let me check what is the form. I get the form. So we are basically doing nothing, but the answer is actually correct for A. Yeah, the A is a correct answer. Now since we actually we will see the value of R in another way, we will actually derive these relations, this thermodynamic relation that we actually know from the entropy of the classical ideal gas, since you know that this equation is followed by the classical ideal gas. So, and as in the lecture, the entropy for a classical gas is given as SUVN, and this is the classical gas where the classical gas particles are identical. So this form is actually called Sackur-Tetrad form of entropy, which is actually N log of EV by N AQ, okay, plus some other things which will be actually a function of internal energy and number of particles. Now we know that P by T, since this first equations, P by T is equal to del S del V with keeping constant S, U and N, that means P by V is equal to del S del V with keeping U and N constant. What we will get if we keeping constant, that means this term actually function of U and N, it will 0, so only this term will contribute, so N it is there, so that will actually become 1, okay, right, del V of log of E by N AQ plus log of V, right. So log of V, this term will be 0, derivative of this term, because this term contains no V term, so it will be 0, derivative of log V will give N 1 by V, so that means P V y N T is equal to 1. That means we actually here derive the state equation for classical gas, and we, since we actually here already implicitly in the formalism it is taken, since it is N is written there, so it is taken care of that the all gas particles are identical. That means if I interchange these two particles, there will be that state will actually not a different microstate from the other, and it is actually classical, not it is in the sense of Fermion is quantum it is not indistinguishable, but it is identical. The indistinguishableness comes in the quantum mechanical particle, but in the classical gas also the indistinguishable is not present, but the identicalness is present there, so that's why this N factor is coming here in Sackur-Tetrad form. So that is all. It is nothing to do with this question, just for your knowledge I am saying that. So we write there, and as in the question it is asked that what is the value of the R. So the value of the R ideal gas is actually 1. So we have done with this question number 2. Now let's go to the question 3. Question 3, right? Question 3. So let me insert the question 3. Okay. Question 3. problem 3. Yeah, let's look very question 3 is actually a tiny looking question. It's very tiny, but is it tiny? Is it not tedious? Let's see. For for Sakut tetrad formula, yeah, Sakut tetrad formula that I am talking in the next in the previous question, the Sakut tetrad formula for the entropy of the classical gas. Okay, answer the following question: what is the change in entropy per particle of an ideal gas that is subject to slow expansion from the initial volume V to the volume 2V, keeping temperature and number of particles fixed? So this point you should notice, you should, and this actually important things here, that you are keeping temperature fixed and keeping number of particle fixed in while fixing the temperature and total number of particle, you are expanding the system. This is called isothermal expansion. This is isothermal expansion. Isothermal expansion, right? So that's then this fixed. So this will V2. So there is a two way to do this to answer this question. So let's see the first question. So first we will use the two things. One is the first law of thermodynamics. First law of thermodynamics. First law of thermodynamics, which is nothing but TdS. Not only first law of thermodynamics, it's actually first law plus thermodynamics plus second law of thermodynamics, because in the second law the entropy is introduced in the second law. In the first law it is actually, let me write it here, first law actually telling the energy equivalence principle, energy equivalence principle. There's no entropy is introduced in the first law of thermodynamics, but in the second law of thermodynamics the concept of entropy is introduced there. Entropy is introduced there. So when you write the energy equivalence formula in terms of TdS is equal to du plus PdV, always keep in your mind, remember that this actually, if we use both first law of thermodynamics, second law of thermodynamics, then actually it will look like this. Here du is the change of internal energy. So let me, here my symbols are quite, so dVq plus PdV. It's not the reduced volume, it is V is not V by N. V by N, I will write V by N always small v. Here it is the absolute volume, maybe it's called absolute volume. So du plus PdV. So TdS is equal to du plus PdV. We'll use that. And second, we use the state equation of ideal classical gas. Since it is ideal, since you can notice it here that it is asked for classical ideal gas. So classical gas is actually PV equal to N KT. KT is equal to K is 1 here, so it's basically N into T. N into T. So that means here what it is asked, here there is one other thing, means mu dN. It is chemical potential. It is mu is chemical potential. So keeping the temperature and the number of particle fixed, right? That means if I keep the temperature fixed, that means internal energy. Hello? Yeah. Yeah. What are you saying that in place of PdV? What you are saying that in place of PdV? Yeah. Yeah, so hmm, hmm. Yeah, you're actually right. Yeah, yeah, you can use the directly formula, but I am actually, I will derive that formula. That's why I'm saying this. Means in means you are writing that formula, but you actually done the step and you get the formula, then you will use that formula. There is nothing wrong about to directly use the formula, so it is fine. Oh, okay. 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 Hmm. Hmm. So now here it is. Okay. Then if we use these two things, means here it is asked that as the question asks that temperature is fixed and the particle number is fixed. That means dn is actually fixed and du actually fixed since the temperature is constant. So that means internally constant. Now one thinks that if these two things is not there, suppose the question is asked this, suppose there's a number of particle is not fixed, then you don't know the actually formula what it is, so you have to use these two formula to get to that formula. So that's here, since according to question it is right. Yeah, you are right. Okay. So as it T ds is equal to, this will be 0, so simply P dV. Now okay, so ds is equal to P by T dV. Okay, here since we know the P by T is equal to only N by V, so P by T is equal to N by V. So if I put it there, N by V dV, so V dV. What is the change in entropy? So volume V1 to V2, ds is equal to N V1 to V2 dV by V n log of V2 by V1. As you are pointing out, it is actually coming that ds, the change of entropy, is equal to actually number of particles into log of V2 by V1. Now as you are saying that if I put it there, so I'll get the change of entropy. Change of entropy, if I change V1 to V2, is actually number of particles into log of V2 by V1. Now it is asked that what is the change in entropy per particle, right? Per particle means change of entropy by n. So it is actually that. Now if we V2 is equal to 2V and V is initial volume is V, so that means log of 2V by V is equal to log of 2. Okay, so that is the answer, and you can again work it out from that. You can write the Sackur-Tetrode form as it is asked here, this Sackur-Tetrode formula, that it is that SUVN. You can put it here that initial condition V1 and the initial V1 is equal to 2V and V2 2V. Now you just subtract these two, you will get exactly 2V. So I am yeah. S equal to so here, okay, here it is here as entropy is increasing, that means the total number of microstate is also increased. So how much the total number of microstate increased is actually captured by this entropy change. So we can always calculate that the change of microstate also from here. S equal, अच्छा, if we write S equal to K ln omega, omega is equal to e to the power k by s It's not thermodynamic probability, it is, no, it's not thermodynamic probability, it is actually microstate. I don't know, it's is it also we call thermodynamic probability, I don't know, but it is actually called the total number of microstate here. Actually in the Boltzmann sense it is total number of microstate. No, not 2 microstate. So its entropy change, the microstate actually changed. You can see from here that ds, it maybe not exact, so d omega will be changes something like a d of that will be suppose ds into e to the power s by k by k. So k is 1 here basically, so k means the Boltzmann constant here, k means the Boltzmann constant. So it is a ds, the change in entropy, into e to the power s, that will be the change in number of microstate. You actually get from here, you can write it e to the power s as. So now what is the change in microstate? That will be simply ds into e to the power s. So it will be the change in microstate. And it is a good question, but it is actually good question. You so total, yeah, you will get, actually you are correct. If you put the ln omega, you will actually get the total number of microstate. Yeah, your statement is correct. As you were saying, since e to the power es is the my previous number of microstate, so it will be omega by omega is ds. Actually the total change in total number of microstate will be actually ds. That's the formula, you can work it up. Microstate actually is varying here, na? So d omega is the change in microstate. So the two things, you can either work with entropy or you can either work with microstate, whatever your convenient way. But as we are in thermodynamics, as we already know there is a concept of entropy, so that's why we actually relate this microstate to the entropy, and we always actually work with this entropy, not microstate. We actually calculate the microstate to reach to the entropy for our convenience, but one can always work with this microstate also. Okay. So that is the answer of the question. Now we'll see the question number 4. So may I put it there? So problem 4, yeah. So it's very problem 4. Okay, it is again a very it's looking very huge. The problem is very huge. Okay, 4. So what it is asked, we showed in the class that the entropy function SUN may be explicitly calculated using this general formula e to the power SUN, that here U is the total number of energy of n indistinguishable particle distributed among m steps. As in the previous class we are working with these staircase problems. If the particles are such that a not more than 1 can occupy a given step, then q is +1, or if b there is no restriction on how many can occupy a given step, then q is equal to -1. The meaning of epsilon j is if there is only one particle in the entire system, then then if this particle placed on the step level j, it is the energy epsilon j. Note that for the formula, that is that epsilon j is to work this formula, you have to notice that this is actually true. To note that formula work only if u, n, m and epsilon j all actually integer, then actually this formula will work, otherwise it will not work. And the question is asked, consider the epsilon j is equal to j. That means if I put one particle in jth state, its energy will be j, and the q is equal to plus 1, okay, and m is equal to 4. Find s u comma n equal to 2 explicitly form above given equation. Also find s n u2 by enumerating all possible configuration. Compare these two result. Okay, it is asked that first from this expression we have to calculate the entropy value. What is our problem? There is four staircase and two particles are sitting there. Now it has been asked in this question, what is the entropy which is non-zero, and we have to calculate both from these equations and by counting from there. Okay, let it from calculate first this. So to do so, we require this multiplicative series m, because n stair are there. So 1 plus, and this is actually q is equal to 1. So we put the q is equal to 1. So that means 1 e to the power. So 1 should not be even there. 1 minus I theta epsilon j is actually j plus phi, and q is actually 1. So what it will be? It will be 1 plus e to the power minus I theta plus phi first term. Second term will be 1 plus e to the power minus I 2 theta plus phi. 1 plus e to the power minus I 3 theta plus phi. 1 plus e to the power minus 4 theta plus phi. Actually I am only expanding this series. I am just putting the value of g here. Now I take that x is equal to, suppose that let x is equal to e to the power minus I theta and a is equal to e to the power minus I phi. So what then it will look be x a, right, plus 1 plus x square a e to the power minus 2i theta means x square a into 1 plus 1 plus x 3 theta means x cube, 3 theta means actually x cube into a, and 1 plus 4 theta means x4. Okay, so that's that. So this is, so to proceed further we will actually need one property of this thing. So we'll prove that property first, then we'll go further. So that is 0 to 2 pi d theta by 2 pi e to the power I u theta minus, suppose n theta. What it will be? It will be 0 to 2 pi. So if u theta, okay, so if u is not equal to n, then we can write it, we can integrate it out and we can write it here as like e to the power I u minus n theta 0 to 2 pi. Actually in 2 pi, since this u and n all both are integers, so e to the power I and an integer into 2 pi is actually 1, and if I put 0 also, so this one's 1, that means this actually becomes 0. So if u not equal to n, for any n it is actually 0, but if u equal to n, then this actually becomes 0, that then 0 to 2 pi d theta by 2 pi, it is actually e to the power 0, that means 1, that is actually this is actually 1. So that means this is nothing but a conical delta function which is even, and similarly phi also. So we will use this property, that's why I am proving this. So you can see here that we can express these terms in terms of the series of xa. So you can do by it hand, but it actually always easy to do it in Mathematica. So I will use now Mathematica to do this. Now okay, oh sorry, so hey, can you see my Mathematica screen? Okay, maybe okay. Blank it is fine, blank fine, blank is fine, but okay, fine. Window is magnification to the right. Okay. Yeah, so what is there? So I have to calculate these things in terms of series. So 1 plus xa into 1 plus x square a plus 1 plus x cube a plus 1 plus x to the power 4a. So that's it. So that's it. That means I have to expand. I have to expand. How many of you actually know to use the Mathematica? No one? No, maybe I don't know. 1 minus x star a, 1 x star a. Okay, first star. You can always do it by hand, but it will take a lot of time to do those all the things, and it may happen that you get one term incorrect. Second term is x square into a, right? Third term is 1 actually minus, oh this is plus, maybe plus 1 plus xa, 1 plus x square a, 1 plus x cube a into 1 plus x 4 a. So you will see that it will expand the whole series, 1 plus ax plus something like that. So now I will collect. Mathematics is actually beautiful. Collect all the terms. Now what it will do? It will collect all the term with same exponent of x. Yeah. So you can see that it is 1 plus ax square plus a square x cube. Now what I will do? I will not expand it in terms of I will expand it in terms of a. Yeah. So what it you can see that I actually get all the things in the exponent of a into, if we just do the algebra, you will get these. So 1 plus 4x x to the power 4 plus a x square, those things. Now what I actually need this formula, you will see it here, that since this is a conical delta, that means this integration, that there is a integration e to the power phi n. Okay, and since x square is x is nothing but e to the power minus I theta, that means okay, I actually get, if I do this in things, so I will get some exponent n m some in alpha nm x to the power n a to the power m sorry, right? Suppose that here what the first term what my alpha nm, can you write now? So alpha nm here, that means with power 0 of a and x, is the component will be alpha nm is actually 1. If m is actually 0, that means a to the power 0 and x to the power 4, that means alpha 4 0, the component is actually 4. Similarly this also, that 1 component, alpha to the power 1 means m is 1 and n is also 1, that the coefficient is 1, and here 4 means if my component the exponent of x is 5 and the exponent of a is actually 1, then the alpha n m is actually 4. So that's why we can write it in terms of alpha n m. With we can write explicitly, but it will need a huge space, that's why I'm keep it short. Now if I put the form of alpha n m, form of x and a, what is the x and a? X is e to the power minus I theta and a is e to the power minus I phi. Okay, e to the power minus I n theta, e to the power minus I m phi. Okay, now that means we actually did this, we actually calculate this part of this multiplication, which actually nothing but this summation n comma m alpha n m e to the power minus n theta e to the power minus n phi. Somewhere it's apart from that, somewhere I have read that in the physics, actually the problem is reduced all its complexity if you can perfectly represent, you can perfectly find some coefficients and you can represent the systems in such a way that all the harder problem will go automatically. So that means if I represent this complicated looking series in very small in very delicate representation, then actually all the calculation will be very easy. Now we will check that. So it is nothing but summation of 0 to 2 pi d theta by 2 pi, 0 to 2 pi d phi by 2 pi. Okay, summation I can write nm e to the power I theta u minus n, because it is there, it is there, that is e to the power I theta u into e to the power this sum. Okay, let it me clearly write that so you can so it is okay, clearly write that, then you can see actually what I am saying. I u theta plus n phi, right, it is there, e to the power I theta u plus phi n, and this multiplicative series actually boil down to this very cute looking expression, which is alpha n comma m e to the power minus I n theta e to the power minus I m phi, right. Now that means summation of n comma m, this summation is nothing to do with this theta and phi, so I can always take this summation outside these integrations. 0 to 2 pi d theta 2 pi, 0 to 2 pi d phi by 2 pi. So e to the power this is alpha n m also actually a constant, is does not depend on these theta and m, as we have seen in this Mathematica. So you know this alpha n m does not depend on theta and m, so you can keep it outside this integration. So nm e to the power, now we will see that what I am going, minus u minus n into e to the power I phi n minus m, right. So all the things, now you actually d theta by 2 pi to the power I theta u minus n, since this is only function of phi, we can take these two separately. So that means 0 to 2 pi d phi by 2 pi e to the power I phi n minus n, right? Now as we have proved that d theta by d pi e to the power minus I theta minus n pi is actually conical delta un. That means we can write is as well the conical delta in m alpha nm. This is integration 0 to 2 pi d theta 2 pi e to the power I theta u minus n. And what is my total number of particle here? Total number of particle is n equal to 2, right? N equal to 2. So if we put n equal to 2 there, if I put n equal to 2 there, that means this will actually give me conical delta n m, right? Since n equal to 2, that means I can write it here. Now I can, that means delta n to delta 2m actually means if my m is equal to 2, actually then this delta function become 1, and for all other cases these become 0. Now you can see that my only term that will survive, my only terms that will survive whose m is equal to 2, that means n alpha n comma 2 0 to 2 pi d theta 2 pi e to I theta u minus m. Now you can see why in Mathematica I collect all those terms whose power is in the power of a, because as we are representing, as I am telling you that things, that as I represent the system, represent my mathematics in a concise way, in such a way that this m actually represent the power of the power of a. Power of a means e to the power I phi. You can see e to the power I phi means a. So what is my m is? M is the power of a, and from here we see that only the power 2 actually survive. All the other terms is 0 because of this integration. That means from the Mathematica, that means these terms whose power is actually 2, whose power is 2, that means h square only survive, other all terms will go to 0. That means only this term will remain there, x cube plus x to the power 4 plus x to the power 5 plus 4x to the power 7 plus 4x to the power 8 plus 4x to the power 9. Okay, now what is asked? See, okay, see which of the following entropy is non-zero? If, okay, that means if I again is u, okay, now that means if I write it alpha n comma 2, now see, let's see, is it 4 5 6 3, which of them is entropy is non-zero, right? Non-zero, that means okay, let me put it and check it, that will be best. So if I put u equal to 4, first u equal to 4, right? U equal to 4, if I put u equal to 4, that means it's become a conical delta n comma 4. That means it will actually boils down to this coefficient alpha, what is 4, right? 4 comma 2. That means I will see what is the coefficient of x to the power 4 and a to the power a square. So okay, let's see, x to the power 4 and a square, what is the coefficient here? It is only 1. So that means my alpha 42 is actually 1. Okay, if my alpha 42 is 1, as it is saying e to the power s u, e to the power s u is equal to 1, e to the power s u comma n is equal to 1. That means what is the value of s u n? Okay, write it in, u equal to 4, n equal to 2. What is the value? It's actually 0 because s u n equal to 0. If I put s u comma n equal to 0, then only it's become 1. So that means this is actually 0. S U equal to 4, N equal to 2 is 0. Okay, that's right, that's all right. So A is 0. Now B, U equal to 5 and N equal to 2. So all the things I have to track down. What is the coefficient with U, x to the power 5 and a square. Now I have to find 5 2, because if I put in place of U 5, then my Kronecker delta will become F5 F5n, and that means my n will become 5. That means I have to find the coefficient alpha 5 2. That means I have to find the coefficient alpha 5 2, which means x to the coefficient of x to the power 5 and a square. So let's see, x to the power 5 and a square, it's against the coefficient is 1. If coefficient is 1, that means if the coefficient is 1, that means my e to the power s, u equal to 5 and n equal to 2 is again 1, and s u equal to 5 n equal to 2 is again remain 0. That means I have to find that n or that u actually corresponding to that. That means I have to find that u whose corresponding delta function will be such that this coefficient is actually not equal to 1, greater than 1. So here what is u6 we have to check u6 and u3. Okay, u6 and u3, u6 and u3. So yeah, so u6 and u3 is not there here. That means the coefficient with those, is it correct? Let me check it again, because if I put it wrong there, minus plus and q equal to 1, is it correct? Is it correct? Okay, 6 2 and is it correct? U6 and 2. Okay, non-zero. I think it's it is not correct, because I put it here a 4 in place of 4. Now it is correct. That's why it's seeming odd to me, because okay, so since what wrong I have did here, that in place of a I put it here 4, because it is not correct. I should have put there a. By mistake I put a, so that's why my expression will be wrong. My expression was wrong. Now I have corrected it. Now let me check the second case, where the u equal to 5. Let me check it. So pardon me for my, I have done a wrong thing there. So yeah, so I have to now check what is the coefficient in x to the power 5 and a square element. Let's check that. So you find that a square and x to the power 5, the coefficient actually 2. That means alpha 5 2 is actually 2. It's not 1. Alpha 5 2 is actually 2. That means this actually all boils down to e to the power s, u is equal to 5, n is equal to 2 is actually alpha 5 2 is equal to 2. That means s u is equal to 5, n is equal to 2, actually ln 2. That means the entropy corresponding to u equal to 5 and n equal to 2 is actually non-zero. Alright, that means we got the we got our answer. That means this B is actually non-zero, and we exactly calculate the entropy, which is ln 2. Now only the work remains there. We have to check it by counting, as we have learned it in the previous tutorial. I have to count it explicitly and show you that it should be matches with my counting entropy. Otherwise, that math will no longer be consistent. Now let it here count. There is a 4 step there. I have to this energy state is 4, this state is 4, this is actually 3 energy, energy of this state is 4, energy of this state is 3, energy of this state is 2, energy of this state is 1. I have 2 particle, I have to put it there such that I will get the energy 5, right? So how many ways I can do that? So one possible way is I put it here, put it there. Another, okay, another is possible, also possible, I put it here, one particle there. Okay, is any other possible way I can get 5 energy 5 with this, with configure these 2 particle in this 4th step? No, there is no other way. That means only the number of possible ways I can put 2 particles in 4th staircase in such a way that my total energy will be 5 is only 2. Now that means microstate is 2. Now according to the Boltzmann equation, what is my entropy should be? Now K beta, K Boltzmann, ln 2. Since we are putting K beta equal to 1, that means our result is N equal to K beta ln 2. And these same results actually we actually got from the calculation, from this tedious calculation that we have done here. That means this formula is actually alright. So we have checked it that if there is a 4th staircase and 2 particle, if I put it there and we want to the total energy of the system is 5, then there is only 2 ways by counting that, and by solving this equation. By solving this equation we also get that our entropy is ln 2. That means our formula, this equation is actually works very well. But one thing so you should also keep in your mind, that when you will be in hurry situation, it's actually good for pedagogical purpose, but it is not good for when you are doing some problem. If the number of particles are very small, suppose that here as it is, you see here that's 2, and the number of staircase is very small, you should always go with the counting method and actually you will get the right result. But suppose that you are humongous amount of particle are there and huge amount of energy state are there, then you can't actually do anything with this counting problem. Then you have to use this equation to calculate its entropy. So that's all. So now we actually did the question number 4. So if any questions are there regarding this question 4, you can ask me, because the thing is now we'll again solve a similar kind of problem. So if any question is there, you can ask me. Yeah, no question is the question number 5. I will solve the question number 5. Okay. Let me question number 5. Question number 5. Okay. Insert figure. Question number 5. Yeah. Now, okay, one thing I have missed it there, that in the previous question it is q equal to 1, and as in the lecture, from the lecture we already know that if for the q equal to 1, this particle actually behaves as its bosons, and if if q equal to 1, the particles is actually like fermions. It can q equal to 1, it can occupy a given step, then in more than one. Sorry, let me repeat it. For q equal to 1, not more than one can occupy a given step. Okay, that means for q equal to 1 is actually fermions, and q equal to -1 is equal to bosons. So we have done a calculation for q equal to 1, and in the next question we will do the calculation for the for the q equal to -1. So it is the question number 5. So what it is asked is the same question, only things is it is different there. We have to do all the calculation with q equal to -1, m is equal to 4, and this is the things. So let it, so again we have to somehow we have to find this multiplication series. Somehow we have to convert this multiplicative series to a series of summations, and if we can successfully done that, then nothing is left. We can always write it in terms of direct Kronecker delta, and we actually get our results very easily. So first we have to express this multiplicative series. So let's, in a very in such a way, means we have to transfer this multiplicative series towards summation series. Okay, so z equal to 1 to m. Now our q is equal to -1. Previously our q is equal to +1, now our q is equal to -1. So put it there, and q is equal to -1, as I am saying, it is means bosons, means more than one particle can, physically it means more than one particle can occupy a single state. 1 minus e to the power minus I theta, and f such a is again j, right? That means no problem. Phi, okay, so okay, -1 there, to the power -1 there, to the power q is there, -1 there. So it means it means nothing but like this, 1 minus e to the power minus I theta into j plus phi. Okay, let me write it properly. Minus I theta plus phi into 1 by 1 minus e to the power minus 2 theta plus phi into 1 by 1 minus e to the power minus I 3 theta plus phi into 1 by 1 minus e to the power minus I 4 theta plus phi. Again I use this, I use this notation x equal to e to the power minus I theta, and a is equal to e to the power minus I phi. So if I write it in terms of those, it will become 1 minus x a, first term x a to the power minus 1 into 1 minus x a, sorry, x square, right? X square e to the power minus I 2 theta, that means x square, right? X square I theta minus 1 into 1 minus x 3 theta means x cube a to the power minus 1, and 1 minus x4 a to the power minus 1. Okay, now since a is equal to e to the power I phi, we actually know this magnitude of the a is equal to always less than or equal to 1, and suppose we forget about the case where this a is equal to 1. If only consider the magnitude of a is less than 1, then actually we can expand all this term with respect in series, Taylor series, we can expand in the series of a. Okay, so since from the experience of the previous problem, we actually know that only two particles is there. That means it's ring a bell in our mind that only we have to keep up to order where the a is a square, because only the term which will survive the integration is actually a square. So we have to keep only the a square order term, right? So we will expand up to a square plus xa plus x square plus some other terms which will be a square. So which will be magnitude of, which will be, so plus some other terms is also there. So is equal to will be not there, is actually not equal, is actually approximately 1 plus xa plus x square plus square plus other terms also there. But as from the previous experience, we know that the other terms will not contribute, only the term with a square will contribute. The that means 1 minus plus x square a plus x to the power 4 a square. Okay, now 1 plus x cube a plus x to the power 6 square, right, into 1 plus x to the power 4a plus x to the power 8a. Okay, now we have write it. Okay, its square should be there. Okay, write it there. Now you can always extract the which term are in order of a square. So you can always do that, but I will use the Mathematica. I will use Mathematica. So right, so here again I will use same things, but I will expand what I will expand. Let's see. Don't worry, I will share this Mathematica code with you guys. So it's basically very simple. So in that folder which I will share, the Mathematica code will be also there. So 1 plus xa plus x square plus a square, 1 plus x into a plus, okay, bracket, I get 1 plus x into a x, okay, plus x square into s square, bracket 1 plus next term x square into a plus x to the power 4 into a square, right? And so after expanding it, nothing is there, all the things are same as the previous problem. So let me expand it. X cube star a plus, is I am right, x square a plus x to the power 4a into a square, 1 plus x cube a plus x 6 x to the power 6 into a square, right? A square is there, a square is there. Okay, a square is there, a square is there, a square is there. So x to the power 6, a square is there. Now last term is it's x to the power, I know it's very boring, but the always that the boring work, the intermediate boring work always lead towards somewhat beautiful result. Then actually the boring works actually worth, doing the boring works worth it. So I know that something beautiful will come. So is a plus x to the power 8 star a square. Expand and collect. I will tell the Mathematica collect all the terms who in the power of a. So as I have told you previously, I only need, since the total number of particle is 2, and since the total number of particle is 2, that means where the previous problem is here, the previous problem is. So let me repeat it here because all the things is actually there. So which term will contribute? What is e to the power I phi minus m? E to the power I phi minus m is nothing but a to the power minus m. A to the power minus m, that means which a to the power m of the series expansion will contribute? Now which m is equal to the n, which is equal to, since it is a Kronecker delta, that means it will become delta 2n. So which m will contribute? Only that m which is equal to the total number of particle. Here it is in this question what it is asked, what is the total particle number? Total particle number is equal to 2. So I have to keep only that term and we can forget about all the other terms, because all the other terms of the series will give zero contribution. The contribution only comes from the term which is a square, right? Okay, then if we expand, that means I actually only write, I will only write the series of a square. What is it's a square? x square plus x cube plus 2x to the power 4, 2x to the power 5, 2x to the power 6, x7, x8. Okay, write it down. Okay, a square, all the other term is there, all the other is also there, and also here also there, but I don't care about that. I already know that only term will survive which power is square or power is 2. So what is this? So x square, x cube. Okay, first two term, x square x cube plus 4x to the power 4, 4, is it 4? Is it 2 actually? 2x to the power 4, 2x to the power 5. X to the power 4, 2x to the power 5, 2x to the power 5, 2 to the power 6, x to the power 7, x to the power 8. I doing nothing, only writing the terms which is with a square, x square, x cube, x to the power 4, x to the power 5, x to the power 6, 7, 8. Okay, sorry. So this and other term also there, but I know that all the other terms will give no contribution. So this term will contribute. Now what I have to do, I have to check for what u it will contribute. As we know, if the coefficient is, as we previously go to the previous case, okay, let me worth to repeat it, because as we know that this integration actually again gives a delta function, a Kronecker delta, which is un. That means all the, what is the n? N is nothing but the exponent of x. So with exponent will be contribute, with exponent actually contribute, that exponent that is equal to u, right? That exponent actually contribute, all the other will not contribute. And if some n is equal to u, then we have to find that what is the coefficient with the series x to the power n, alpha to the power n. Okay, that's okay. Then what is that? That means now here previous question, sorry, it's previous question. I have to find what is the value of u equal to 6, n equal to 2. Now you know u equal to 6, u equal to 6 and n equal to 2. Alright, u equal to 6 and n equal to 2. That means I already know that I have to write the coefficient of what? I know that's coefficient of alpha 6 2. That means the coefficient, if I expand these things, expand these things in terms of this e to the power I theta and I phi, I have to only keep the order of keep the term, the coefficient. What is the coefficient with x to the power 6 and a square? What is that? X square, x, it is 2. That means my e to the power s u n is nothing but 2. It's actually exactly equal. It's not approximate. It's actually exact equal, right? That means my entropy, what my entropy is equal to ln2. Now you see that I done all these tedious calculation that give me a simple relation which is telling me that a is equal to ln2. Again it is what? For u equal to 6, n equal to 2. So first part I have done. Second part, u equal to 4, n equal to 2. Let's check. U equal to 4, n equal to 2. U equal to 4, n equal to 2 means I have to find alpha 4 2. That means the coefficient x to the power 4 a square. What is the coefficient? 2. So here again a e to the power s u comma n is equal to 2. That means a is equal to ln2. Now without doing anything, I can know that the answer will be a, because all the options that's only have 2 ln2 correspondingly first or epsilon 1. But for the pedagogical purpose, I will also show you what is the value of u7 and n2, right? u7 and n2. u7 and n2 means I have to find the coefficient of u7. This the coefficient is 1, right? E to the power s u comma n is equal to 1. That means what is the s? S is equal to nothing but 0. That's it. That means the question A is my answer. Now because previously I have choose the correctness of this question, now again I will choose the correctness of this question. So let me check here. There is a 4 particle is there. In the previous case you can you can see that only one particle can be there in one state, right? It's a fermion kind of things, fermions. Now here since bosons in single state, multi-particle can be there, since no restriction how many can occupy a given state. So that's it. So that means I have to count how many ways I will get 6 4 6 and energy 6 and 4 2 I deleted this. Do then as 2 3 4, this is 4 energy, this is 3 energy, this energy 2, this energy 1. One possible way is I put this 2 particle here. Another possible way, I actually 2 particles, so I actually get 6 energy 6, and I 1 particle here, 1 particle there, then also 6. That means only 2 possible ways I can get 6 energy if I arrange the 2 particle in 4 staircase. That means here the total number of microstate is 2, my entropy is ln2. So first actually it is actually matching with my result that I have calculated here. That means my once again it's actually telling me that my formula is actually consistent, right? And second let me quickly check the second also, where this s equal to 4, right? 4 and 2 particle I put in such way I will get extract energy, right? 4 3 2 1. So always I put 2 there. So this is one possible way. Another possible way is you actually know 1 here and other is here, so that's where I will get energy 4. That means again the 2 possible ways. So total number of microstate is 2, entropy will be ln2. That means it also tells me that my formula, that is this, actually correct. But there is a warning that if you only have very few number of stairs and few number of particles, you should always go with this counting thing, that you actually count the things, and it will require very few it will require very few times. But in place of that, if you do this calculation, you will get a long time. But when suppose that you want to calculate the entropy, suppose 100 particles there and 200 staircases there, then this actually the savior will be this formula. That's all. Now since the time is over, so there is another question is also there, which is actually which you can also do in the similar fashion of question 4. So I will not do that question 6 here. So that's the all things that that's the all things that I actually did in this course, so did in this tutorial. So that's it. So if you have any question regarding the calculation, you can ask me, or you can left the meeting. Is there any question then? Okay, no question. Abhiram, is there any question? अरे मेरा प्रॉब्लम था, कोई इशू था, वो ड्रॉप कुछ इशू के लिए मैं कर नहीं पाया. मैं आज रात तक वो अपडेट कर दूंगा पक्का. ठीक. अच्छा, क्वेश्चन का ज़्यादा सेट मतलब समझ नहीं पाया. चेस्ट पेपर से अच्छा ठीक है. मैं कोशिश करूँ, क्योंकि हमारा इंस्ट्रक्शन यही है कि जो प्रीवियस ईयर का जो असाइनमेंट था वो सॉल्व करने के लिए, अगर तुम तुम बोल रहे हो तो मैं कोशिश करूँगा कि क्वेश्चन अदर जगह से भी कलेक्ट करके मैं डाल दूँ स्लाइड में, मैं करूँगा नेक्स्ट टाइम से। स्पेशल बुक में तो पाथरिया इज वेरी गुड बुक फॉर दिस स्टैटिस्टिकल इंट्रोडक्शन टू स्टैटिस्टिकल मैकेनिक्स। That's, and you can always go with that the class notes of the David David Tong, the class note of the David Tong. You can Google it, the class note of the David Tong. You actually find it there in Google. So it's actually very good note for introductory purpose. For introductory purpose, it's very good note. So that's it. So if there is okay, so if there is no question, I will end this meeting here. Okay. Thank you for joining.